Software Engineering Radio episode 25, Software Architecture Part 2. Okay, welcome to another episode of Software Engineering Radio. This is part 2 of the Software Architecture series. On the microphone is Markus.
And Michael.
And I think this is another one of the relatively theoretical episodes where we talk about concepts. In later architectural episodes, we'll probably talk more about practical issues. The first thing we want to talk about in this episode is something we call quality attributes or quality characteristics or quality requirements or non-functional requirements with regards to software architecture. So when you build a software architecture, then you probably always have to make a lot of compromises and you have to balance several requirements. And those requirements can be grouped into several different categories. There is, for one, the runtime requirements, runtime characteristics of a system, things like performance, scalability, availability, usability, and security. Then there is the structural attributes, things like maintainability, portability, reusability, integratability, and testability. And then we have the business aspects, things like time to market, cost, lifetime, and rollout schedule. So we'll basically first talk about the illities. Performance-ility probably is the term that's still missing here. So, Michael, do you want to start explaining performance?
Yeah, I will start off with performance, and just to mention that, like runtime attributes, there's also another term sometimes regularly used called operational requirements. This term got used by Kevin Henney, for example, in an article he called Inside Requirements. And structural attributes like maintainability and portability, he calls them developmental requirements. Okay, right. But coming back to performance. Performance, well, has two kinds of flavors. One is latency, so basically the time a system needs to react on an external event. And the other is throughput, on how many events, for example, per second get processed through the system. And latency is one thing that is especially important in real-time systems, in soft real-time systems. It's not a big fault when a deadline is missed, so when the latency gets exceeded, but in true hard real-time requirements, it's actually a fault then when the latency gets too large and the deadline gets missed.
On the other hand, the throughput way of measuring performance is more relevant for transaction systems and business systems as opposed to latency in embedded systems.
Okay, and whether you achieve high or low performance is dependent on a lot of things. It's dependent on your hardware, on how well you designed your algorithms, what kind of algorithms you used, what kind of communication overhead you have inside, and the memory available, bandwidth. So all impacts in some way or the other the performance of the system.
And it is important to mention that performance is defined, as we explained before, at a specific configuration of your system. So if you know that, for example, you have to process a certain number of events in a real-time system, you can tune your system so that it optimally performs for this set of events. So the performance is specific for a certain well-defined configuration of the system.
Yeah, the performance requirement actually has to be associated with some well-defined use case and configuration so that you actually can measure then in your system test or in your final integration test whether you actually achieved that performance. So just a single performance number without giving a use case wouldn't be a good requirement for a development team.
Another reason why it's important to stress this configurations thing is if we compare performance with scalability, which is the next point we want to talk about. Scalability describes the fact that a system can keep its performance or degrade only slightly if you put more load onto the system. Now, of course, if you have a certain configuration and the system performs well, then you cannot expect to add 10 times the load and the system has the same performance if you keep the hardware the same. So, of course, scalability includes the idea that you can add twice as many machines and your performance is the same as before if your load doubles. Or said the other way around, if you keep the system configuration, your hardware, your resources the same, then if you add twice as much load, the system should only get twice as slow or half as fast. The degradation of performance over the load should be linear or nearly linear. And that is especially important for enterprise systems where the environment, the load on the system is not always known. If you start a website and you expect that you have, 1,000 hits per minute or hour, doesn't matter, and then your website becomes more popular and you get 5,000 hits per whatever time period, then of course you should be able to add a reasonable amount of hardware so that things don't get too bad or too expensive respectively.
The next quality attribute we want to discuss is availability. And availability is basically a factor, a percentage calculated by taking the mean time to failure divided by the mean time to failure plus the mean time to repair. So availability means that your system should be up and running at least that percentage of the time. Reliability, on the other hand, is defined solely by the mean time to failure, so how often a failure occurs in your system.
And that's really important to mention. If you have a system that fails every hour but automatically reboots using some kind of watchdog, and the reboot only takes a second, and people don't notice this outage time of 1 second, then you probably don't have a problem. There are many, or at least several embedded systems which do crash from time to time, but their rebooting time is so quick that the availability is still very high, right? Yeah.
So you also have to define what actually a failure is. So is a failure already when you miss a deadline, like in a real-time system? Or is low throughput also considered to be a failure when the system is basically not responsive to user requests anymore?
Right, so one should maybe extend the definition. We said before that the availability is more or less the time during which the system is up and running, free of failures. Maybe we should add, and with a specified quality of service, right?
Yeah,
so
right.
Because if a degradation of quality of service constitutes a failure, then it's really, really important to give this term, to mention that term prominently.
The next attribute we want to discuss is usability. And usability has some also multiple kinds of flavors. For example, learnability. How long does it take for an end user to learn on how to work with the system? Or efficiency, on how efficient can a user actually operate? How is the user interface designed? How well can the user get its job done? The other thing is at developmental time, how easy is the API to learn? How does the API protect the programmers from making mistakes? This is basically about a programming model that the API supports. Is this awkward, or is it just straight and easy to get right, actually?
Yeah, it's really interesting to see these two terms, learnability and efficiency, because it's often the case that a system that is easy to learn, so it's quite obvious how to use it initially, is not always very efficient if people have to work with it a lot. So this is some of the reasons why web UIs and rich clients are often considered kind of more or less rather different concepts, because web UIs are easy to learn, but they're not very efficient to use if you have to do a lot of work with them. So those two specifically are often kind of in conflict.
The last kind of flavor is the memorability, if that term exists, and that is basically how well can a user remember on how to achieve its task. Does he have to search the buttons and menu items every time when he uses the application and didn't use it for a while? Or is it just so easy that he doesn't need to look up into help and browse around to find the right icon?
Right. And again, this probably ties into learnability, because if it's easy to learn, then it's probably also easy to relearn, which is more or less the same as memorizing what you did before. The next requirement is a very diverse one, which is security. And we probably have to do a couple of episodes on software security separately, and also you should listen to the Security Now podcast, by the way. But the point is that there are different kinds of security. So first there is the authentication problem. So people or users that haven't properly authenticated to the system shouldn't be able to use it. The other thing is authorization. So once your user has been authenticated, so is basically allowed to use your system, you have to specify or determine which parts of the system he can use and how, which resources to access, which data to access, which functions, which features to use. This is called authorization. There are other kinds of securities. One is obviously the thing that if you move your data over a network, you should probably encrypt it. You should be safe against various kinds of hacking attacks, things like trying to exploit buffer overflows, or another problem is denial of service attacks. If you have a system that faces the web or a network, your system should be robust against denial of service attacks, although this is non-trivial. Do you have anything else to add to the security thing?
No, I think you covered it from a high level, and details will come later in later episodes.
Right. So maybe one last comment on security. There is a common understanding in the architecture world and also in the security world that it's probably not possible to add security after the fact. Security should be designed in from the start, and that's something that many people don't really take to heart. And so many systems are not very secure because people thought, oh, we can add security after the fact, and then it didn't work out.
The next developmental requirement is maintainability that we want to discuss, and that is basically how well can you extend or change your system after you have deployed it once. And for this, it's basically about refactoring. That is a term which got used lately in the last few years intensively. And it's about removing features, it's about changing features, changing implementations, extending it to new scenarios, new requirements, or just adapting the whole solution to a new environment, like a new application server platform or a new operating system.
A specific kind of maintainability is portability. You probably want to be able to run the system on various kinds of environments, specifically on different operating systems, on different hardware, on different networks. This is especially important in the embedded world, where you usually have various configurations of systems running on different hardware platforms. At least in the automotive world, we've had this problem regularly, and you have to do a lot of non-trivial things to be able to run your system on different environments. The point is, of course, that you should, if you talk about portability, then you want to be able to run the system ideally simultaneously on those different platforms. Simultaneously means that you shouldn't have to manually change your code base in order to run it on different environments. So maintainability, portability, both of these are about managing variabilities and handling variabilities and representing variabilities in your system. And the reason why I mentioned that is that we will have a separate episode later in this podcast about variabilities, and then even further in the future about product lines, which is basically about formalizing those variabilities even further.
Another term we want to define here is reusability. And this basically specifies how easily parts of the system can be reused in another system. And that is also, of course, the general reuse topic, and especially important in the context of software product lines, software product families, where you have multiple products based on the same components, based on the same core assets, and you want to reuse those parts maybe in slightly adapted or configured versions. So reusability is not just about inheritance, what basically OO tried and in my opinion never truly achieved reuse, but it goes even further of using basically all means to ensure that a software component can be reused at a later time.
Another one is Integrability. It's also a rather strange term, I guess. So it specifies how easy it is to develop parts of the system separately and integrate them later on. Modularizability could be another term. So the point is, if you have a big system, then it's unlikely that you can develop all parts of the system in one go, in one team, at one location, and you have to make sure that the separate parts that you have to define can be well separated, and then later on integrated together again well.
Testability is the next term and the next requirement we want to discuss, and this is basically about how to make sure that you can demonstrate that your system does what it is supposed to do, that you can test it easily, and that starts off with unit tests, module tests, until you reach the integration and system tests. Depending on how large and complex your system is, you might rely on all of these testing steps. And the architecture, it's a concern, it's a property of your architecture on how easy it is to test it, to verify that it does what it's supposed to do.
Right, and again, this is a big topic that we'll cover in future episodes specifically. There is one rather recent trend which says that if you build your system so it's easily testable, then it's probably well structured. So using testability as a means to drive the quality of your architecture is something that has gained a lot of importance recently, and we'll cover that in later episodes. So now we covered runtime and structural quality attributes, or operational and developmental attributes, and we briefly want to mention some of the business aspects, although we really want to do that only briefly because this is a technical podcast. We don't want to talk too much about business things. But the point is that if you consider things like time to market or cost or the lifetime or the rollout schedule of your system, then often those business-related quality attributes or architectural attributes are in conflict with some of the technical attributes we discussed before. And in a minute, we'll explain some of these conflicts a bit in more detail. The point is that those business aspects are typically represented and enforced and taken care of by non-technical people, i.e. managers. And that's also why some of them are in conflict with some of the technical terms, because different people, different interests, different groups represent them. So you always have a conflict of interest, or at least a conflict of viewpoints and priorities.
Yeah, those terms are time to market. When are we expected to deliver our solution to the first customer? It's cost, how many resources, how many developers can I afford, how many managers, what kind of effort do I spend for testing. It's about a rollout schedule. Do I have to be full up and running, no failures, no bugs inside when I start to enter the market, or can I afford to have some bugs in there and do the final system testing with the customers, as some big software vendors actually try to do? Yeah, Markus?
I just want to add that something we didn't talk about before is quality in general. So there might be systems which do have bugs, but you will leave them in the system because time to market is more important. So another quality attribute is just the number of bugs in your system, and you might specifically want to make compromises. So you might want to leave bugs in the system because fixing them would be too costly or would basically kill your time to market.
Yeah, and there's something that we software people just learn to accept, that basically no system is free of bugs. You will always have a bug in there. It just depends on how critical that bug will be and how often or when it will occur.
Right. A bug that nobody notices probably doesn't matter.
Right. So I had an idea about, you mentioned that only non-technical people are responsible for those. What I really liked is when the technical lead or the software architect actually got involved in those business aspects and was at least involved in the discussions and about that, so that he knew under which pressure he actually is, and what are the concerns and basically the frame in which the development team operates.
Right, I agree completely. The point why I mentioned that before is that in many projects, that what you described is not the case, and therefore a lot of problems result. Of course, in a well-managed project, your technical leaders will at least the leaders will care about those business aspects. Absolutely.
When development is involved in this discussion, then it's just easier to deal with the short time to market that we always have. When we just know what the constraints are, it's easier to deal with them. So one suggestion would be to make those business aspects quite transparent to the development team. Well, not stress the development team, but keep it informed, make it not worry about it, but make it know about it.
Exactly. I think this distinction is really critical, that you have a kind of firewall between the requirements in your customer and your developers. That doesn't mean that developers should ignore these things or not be told, but somewhere there has to be some separation so that people don't get, as you said, don't get stressed all the time. Right. As we mentioned before, those quality attributes are, of course, in an ideal system, you will have 100% of all of them. Well scalable, no bugs, very maintainable. But in practice, that's often not realistic. So you have to strike a compromise and basically say, okay, we explicitly reduce this ility and therefore increase another ility. And so as a consequence, your system might probably be, for example, less maintainable, but it might perform better. And we'll come up with a couple of examples and specific conflicts in a minute. The point is that you should make those decisions explicit. I mean, you shouldn't just build a system and then at the end notice, oh yeah, it's not maintainable, but it's fast. And that might not be what you want, but rather you should discuss these things in the beginning and say, okay, our focus is on, for example, performance, and therefore we'll explicitly make compromises with regards to maintainability or portability. So, yeah.
I actually like to make my customers a priority list of all the illities so that I know on which to focus first, on which to focus next. There must be just a straight order and not just everything in parallel. Well, achieve scalability and performance and maintainability at the same time. This is just not possible. You have to balance the forces and there will be a preference. There's no way around it.
Right. It's also one of these things where you often have to educate your customer and really make them think about what they want and where their priorities are.
Right. And another term that comes actually a bit from the pattern community is balancing forces. And so balancing forces in software architecture is comparable to balancing forces in applying a pattern to a design problem, just at a larger scale.
Right, so you have to make trade-offs.
You have to make trade-offs, right.
Yeah. Okay, so let's maybe come to a couple of typical compromises or trade-offs you have to make when looking at the relationships between a couple of quality attributes. And again, each of us will come up with an example in turn. The first one is performance versus scalability. So, for example, you might be able to fine-tune your system to a very specific environment so that it comes up with a very, very optimal performance. But scalability might be bad, because if you add additional load, the system, queues might be full, or some algorithms might run out of their optimal performance characteristics, so the system might not scale well, although it performs very well for a specific situation.
The next conflict is performance versus maintainability. And here, for example, to achieve high maintainability, a designer, developer might just decouple everything, introduce a lot of interfaces. For example, I saw just recently a so-called service-oriented architecture, and that was a service-oriented architecture down to classes, down to little small responsibilities. And the performance, of course, then was not acceptable anymore at all. So this was just taking SOA to an extreme, and where maintainability might have been good because everything was separated and with its own interface, actually its own remote interface, it was not performing anymore.
Right. As usual, if you overdose any medicine, it's probably going to be bad for you. So, being the medicine here. Another thing is performance versus portability. Portability, as we said before, is basically a kind of special case of maintainability, So if you want to be portable, you usually have to add all kinds of indirections, microkernels, layers that hide some of the specifics of your underlying platform environment. And of course, this layering and this separation of concerns costs performance. There is one way how you can maybe solve that. For example, if you have a C program that should be portable, you can have all the various platform specifics, separated using if-defs and these kinds of things. Then the system might be portable as well as perform very well, but then it's probably not very maintainable because your code is cluttered with all those if-defs and stuff. So again, you have to make compromises somewhere.
The next is availability versus performance. And for availability, a typical thing which is done to achieve high availability is checkpointing, that you in your regular call and control flow of the system, you store the state, you persist state, so that when failure would occur, it would be easy to resume again. So to minimize the mean time to repair, to be up and running again in a consistent state. And so the problem here with performance then is that those checkpoints, that persisting those checkpoints can be quite expensive. And so if you use checkpointing too extensive, your performance will be bad at the end.
Another example for this particular conflict, availability versus performance, is also, for example, if you have a system that should be very, very highly available, then you probably have to have redundant components like redundant servers or, for example, redundant databases. And depending on the level of availability, you would actually have to have hot standby. So that means that you have the same information on both components. And that, for example, means that whenever you do something in the database, you actually have to do it in two databases using, for example, the XA transaction coordination protocol for two-phase commit. And that, of course, introduces an overhead and your performance will be reduced. To illustrate one of the conflicts between the technical and business aspect, if you want to have a system that is more available, then you have to make sure that there are fewer bugs in it. You probably have to have redundant components, as we mentioned before, and that of course drives cost. So the more available and the more reliable a system should be, the more expensive it's going to be. And that's nicely illustrated if you take a look at systems like I don't know, I never saw the software of one of these, but for example, the space shuttle or nuclear power plants or live devices that keep you breathing during a medical operation, medical treatment. Of course, those systems have to be very, very reliable and very, very available, and developing those systems is extremely, extremely expensive.
The next conflict is about usability and versus security. And here a simple example is when you increase the security of your system, you might require the user to fill in all kind of passwords and tokens and generated IDs. And this then really conflicts with the usability when a user like every day has to do that procedure to access its data or to read its email. And here features like single sign-on or similar mechanisms help and basically balance kind of those two forces. You get high security, but you have to trust that the one signed in user actually stays to be that user and has the sufficient rights.
The classic example of this usability versus security is Microsoft Windows, right? They added the firewall only, I think, in XP Service Pack 2 because, they turned it on by default. Because earlier, Microsoft kind of decided that they didn't want to bother their users with all those, prompts that says, hey, there is some connection coming in, do you really want to accept the connection and stuff? So this was a classical conflict between usability and security. So before we finish, I guess we should mention that there is also sometimes a relationship between those quality attributes where you don't have a conflict, but rather where things support each other. For example, maintainability can help availability, because if your system fails, if you have a maintainable system, it's faster to fix the problem. So your mean time, or your time to reinstall or rerun or to fix the system is going down, so your maintainability goes up. So it's not always just conflicts. So at this point we want to stop for today. This concludes the episode number 2 on software architecture. In the next episode on software architecture, episode 3, we'll be talking about how you can actually achieve some of those quality attributes and also show how to resolve some of the conflicts that we mentioned in this episode. So thanks for listening. See you next time. Bye. This was another episode of Software Engineering Radio. The Software Engineering Radio team wants to thank Henning Pauli for providing the music, as well as Libsyn.com for hosting and bandwidth. For more information on the podcast, past episodes and feedback, go to se-radio.net.